All right, now that we've taken a look at one approach that we can employ for calculating the length of a row, or all of our rows, in which we can then determine the width of our benches, let us look at another approach. So I'm going to jump back over to the whiteboard, and as I had already mentioned, with this particular approach, we're really just interested in calculating the distance between 2 points. So let me go ahead and come over here real quick, bring up another one of these guys, and let's draw out very simple shape, top-down view once again. Something like that, it's close enough. And again, we'll give this guy 2 rows. Now we know that we copied with our profile curve a point to there and to there. And this is the profile curve that we then basically swept around to there and there, where we were then able to use a point node or point SOP to average the 2 positions so that we could come up with our center positions. Well, with these 2 points, technically, we can easily come up with the distance between them. And what is the distance between them? That is the distance we're looking for. So that would be the length of that row. And the distance between these 2 points would be the length of that row. So if you recall, coming back through the network, we came down over and into a delete SOP that was used to isolate our 1 point. And then from here, if you recall, basically we took this guy out, we transformed him, and we took this guy and we ran both of these into a point SOP. And it's on this point SOP that we were able to, if you recall, on the position parameter, use $tx plus $tx2, and take these 2 guys and divide them by 2, since we were finding the average of 2 things. We were able to apply this to x, and then to y, and then to z, and then boom, coming out of this, we now have our points positioned in the center. Well, coming into this point, we have our 2 points, and we have each of their points' location in 3D space with the $tx and the $tx2, y and z, of course. So with that, we can employ Pythagoras' good old theorem to the calculation of distance. What am I talking about, for those of you that may be saying, huh? Well, in 2D space, where we're just dealing with x and y, so a simple plane, if we had 2 points, and I said, I need you to find the distance between these 2 points, would actually be pretty simple. Coming out in x direction here, we would know how far that point is. And we would know how far up in y that point was. With that, basically, we can establish a right angle triangle. Now, since we know how far over in x this is, let's say that this is 4 units over, and we know going up in y we had 5 units, and this point here just happened to be at the origin, then actually let's go with 3, and then this guy over here would end up being 5.
Nice. How
How would we go about calculating this guy? So let's say that this is the guy we're looking for, because this is the distance between the 2 points. Well, Pythagoras' theorem states that a squared plus b squared equals c squared. This would be a, this would be b, and then over here would be c. So a squared plus b squared equals c squared. So 4 squared plus 3 squared gives us, well, what's going to end up being
plus 9, which is 25.
Look at you go, my math man!
And 25 is 5 squared.
25, and 25 is indeed 5 squared, which is, there you go.
Sweet.
So, of course, let's make this look a little simpler, because when we want to solve for the distance, in this case we're just saying it's c, you don't want to say, I want to find the distance squared. That's a little awkward when we can take and simplify this a bit. So if we were to take the square root of both sides, we will have simplified the formula down to c equals the square root of a squared plus b squared. Because the square root and the whole square thing, get rid of the guy. All right, so now a squared plus b squared, that's fantastic, but this example was dealing with finding the distance between 2 points on a plane. Now we need to deal with finding the distance between 2 points in 3D space. And this is really simple. All we do is add in one more parameter. So I'm going to change this to say d instead of c. So our distance is going to be equal to the square root. I'm not going to take the time to prove all of this. Just believe me, the formula is correct.
When you adapt the Pythagorean theorem into
squared
3D, it becomes
plus
like so.
Y squared plus Z squared.
And the proof is really simple if you want to check that out on the net somewhere.
Yeah, basically just use and calculate one triangle that you end up using to the distance or the side between that becomes one of the sides of the
next
final triangle.
And we end up with this as the result.
Exactly. But we know that this is the formula we need to use, but we've got 2 points that using the Cartesian coordinate system gives us an x, a y, and a z. But we've got 2 x's because we've got 2 points and 2 y's and 2 z's. So how do we come up with our true x, y, and z? Very easy. All we need to do is take x, and actually I'm just going to go ahead and I'm going to start writing out the whole thing.
Cool.
Pause for a second. So if we say take $tx and we subtract away $tx2, so the input coming in over here, this right here is going to give us our x. Now we square it. So that represents this guy right here.
And we can see that that's the case because if we take our tx and we subtract from it tx2, that's going to give us the distance in x between those 2 points. And that's what x means in our equation where we have x squared.
Exactly. So now we can just continue on with add to this. We need to calculate y squared, and same thing. $ty minus $ty2, second input, and we square it, and we add to that our final, and let me go ahead real quick and we'll just clean this up. Switch back over for me. There you go, Photoshop. So $tz minus $tz2 squared. Now, if we were to take the square root of this whole guy, that you like those little things, don't you?
Yeah, it's just a really long expression now.
That is going to be our true distance between the two. But wait, there's more. In this particular case, that distance between the two is the length of a given row based off of the 2 points on them. And we can simply use that information back up. Ooh, I'm using the word back up. That means we're going to have to do another stamp.
Sweet.
Back up on our box to drive size X. So how do we do this? How do we actually go about calculating? Where does this go into our node network over here? Well, we know that we have this particular data available to us in this node. But how am I going to go about calculating that and storing that information? This is where we're going to need to create an attribute, and then we can store the result of this formula into that attribute.
Exactly, because the point stop is extremely powerful and it's designed for modifying existing attributes, be they attributes that come on points by default or ones that we create. So we can't create a new attribute.
You said the key thing, on existing attributes.
Exactly, so we can't create a new attribute on our point stop, but we can modify an existing one, which is what we're going to do here.
So to make an existing one, we'll simply jump up in our network and insert in, and hang on, I'm actually going to rearrange this a little bit more. Actually, let me just redraw all this, because we need to do it up just a tad bit higher. Photoshop. Actually, doesn't matter.
It doesn't actually matter.
I don't know why I'm wanting to put it up there for some weird reason.
That's
I know
what we're going to do when we
did it. That's the way we did it. The reason I got quiet for a second, I was thinking, it doesn't matter.
No, it really doesn't matter.
Why am I redrawing this? But too late, redrawing it, so that's just the way it goes. Wow, that's impressive. I managed to just kind of confuse myself for a second.
Cool.
But this is the way we are going to put it together. So this is an attrib create SOP. So attrib create.
And we've seen this guy already.
Yep. And with it, we're going to create an attribute. Its name is going to be bench length. It is going to be of type float. Now here's the most important thing. It's class. We're going to set its class to point because we're creating the attribute for each point in the data that is coming through this network here. So class is going to be set to point, and by default it'll have a value already in there of 0. So every point down here is going to have, and Steve can show you this in the spreadsheet, is going to have an attribute called bench length with a value of 0.
Awesome.
So now we need to simply create this expression, and we'll create this expression here on our point SOP. We'll just simply go over to the custom tab, and on the custom tab we can specify an attribute, and then we can give it scalar values. And so we'll just put our expression in there.
So now on the point SOP we can specify our bench length, we can overwrite its values with this expression, and that's going to store the value of the length for each point for the row that it represents.
Exactly. And now we already know that this is coming down to the template portion of our copy. So with the template portion of our copy, we'll just come over to stamp and say, look, we need to stamp this information back up. So to gain access to that information, we're simply going to use a very simple expression that's going to say, let's take a look back up here at this guy and look for an attribute called bench length, and let's get the correct value on bench length for the point that we're currently dealing with, and we'll stamp that all the way back up. We'll use that back up at the top. We'll have the correct length.
Nice.
So all we've done here really is added in one other node that we did not have in the last example.
And that was the attribute create, not the point. Sweet.
Just kidding. So we've added this guy in right here, and we've added a relatively simple expression when compared to the last expression.
Yeah.
And then back up, that's it. That's the same principle in regards to we're taking data, we're pumping it back up to be used on size X for the box. There, you like that, Steve? Okay, your turn.
Cool, so let's jump over into Houdini.
All right, let's do it.
And implement this.
Okay.
Where's the mouse? Sweet. So we're going to take our points that are coming through from isolate bench points, and we're going to create a new attribute on each of these points. And we've seen on the whiteboard that we're going to use an attrib create SOP to do this. So I'm going to right click on the output of isolate bench points, and I'm going to wire this into an attrib create. Enter to accept that, and enter to place that into our network. The name of the attribute we're going to create is going to be bench length. And we're going to create a point attribute with a data type of float, since we're dealing with lengths, and the lengths are going to be a floating point value.
Right.
Now by default, the value is going to come in with a value of 0, and we're going to overwrite that when we get down to our point SOP. Now, just to prove that we have this attribute and all of the points have this attribute with a value of 0.
Very important what he is about to show, just so that you can get comfortable with doing this.
Yeah, and it comes in extremely useful when you want to check exactly what's going on with attributes. Have you created an attribute correctly? Are you assigning the values correctly, etc.? If you right-click on a node, we can come up to the spreadsheet, and we've seen this before when dealing with the attribute we created for the pool, but I only really briefly skimmed over it rather than talked about it in depth. If we come up to the spreadsheet, we can see all of our attributes for points, for vertices, primitives. We're dealing with point attributes, things such as position, which are on the points by default, and our newly created bench length. And for all of our points, bench length is currently set to 0 because its value over on the attrib create SOP is set to 0. Now we can come down to our point SOP, and where we've got here existing parameters such as, or attributes such as position, weight, normals, etc. If we come over to the custom tab, we can specify our own custom attributes that we want to set on the point SOP. And the attribute we wish to set is the one we've just created, which is called bench length. So we can set our bench length parameter with a scalar value, and since bench length is a single float value, we're only going to set the first value. So I'm going to Alt-E to bring up an expression editor. And let's just see, what if we were to set this now to a value of 1 just to begin with, and I apply that. If we right click on our point SOP and come up to the spreadsheet, we'll now see that our bench length has been overwritten to a value of 1. Well, we've seen that instead of just a value of 1, we want to use this as an expression to calculate the distance for the point, for each point, basically for the row that it represents. And we have the information we need to do that. We talked about this on the whiteboard because we've got this set of points and this set of points coming in. If we find a distance between those 2 points on the point SOP, we're going to have the length of the line that the point represents. And this is really nice and easy. So we're going to take the square root. We're going to take the square root of tx minus tx2 squared plus ty minus ty2 squared plus tz minus tz2 squared. So to do squaring, you have a couple of different options. I'm going to use the power expression because it keeps our overall expression a little bit shorter and cleaner. So we're going to take the power, and what are we going to take the power of? Well, it's $tx minus $tx2 is what we want to have something to the power of, and we're going to be squaring that, so the exponent is going to be 2. So we're going to take $tx minus $tx2, and we're going to square that, and that will close off our power expression. And we're going to add this to the power of $ty minus $ty2 squared, and that will close off our other power expression, and add that to the power of $tz minus $tz2 squared, and close off that power expression. So we've got tx minus tx2 squared plus ty minus ty2 squared plus tz minus tz2 squared. Take the square root of all of that. And if we accept this and bring up our spreadsheet, we can see that we've got on our bench length parameter, we've got a 2.6, 3.4, 4.2. So for each point as we go back, our bench length is getting longer. So it looks as if this is working. So now if we stamp this back up, we should double check, are we getting the exactly correct values that we're after. So I'm going to close out our spreadsheet and come down to our copy SOP. And we need to make sure that we're stamping. And before we stamped our row number up when we're dealing with our other way of calculating this time I'm simply going to stamp that bench length parameter up. So I'm going to create a stamped variable called length, and for the value I'm going to use the point expression to grab the length of the basically to grab the attribute value for each of those points. Just scale that down so we can actually see the name of the SOP that we're dealing with. So point takes in 4 parameters. The first is the node that we're going to reference those points on. We're going to reference our average positions point SOP because we know when we right click and bring up the spreadsheet for this guy, we know that we've got our values set here. So we're going to say, okay, I want to reference point attributes on this particular node, and that's the node we're going to specify. So we're going to specify our average positions point SOP. What point number are we going to deal with? Well, we're dealing with wanting to grab the point that we're currently copying to, and we know that that's a local variable available on our copy SOP called $pt. So when we copy to 0.0, we'll put 0.0 in here and reference 0.0 up on here, and we know those point numbers correspond. Then when we're on 0.1, 0.2, 0.3, we're going to reference different points up here, so we're going to get a different attribute value for each point that we copy to. What attribute do we wish to copy? That's going to be our bench length, which I do believe I need to put in quotes. And finally, what index are we going to be grabbing from that attribute? Well, we only have a single value, so it's going to be index 0, whereas we saw before if we have an x, y, and z, we have 0, 1, and 2 as indices. So we're taking the bench length attribute on our average position SOP for each point that we're referencing. So if we accept that, and then come back up to our box, we can now reference that stamped variable to grab each of the bench lengths in turn. So we can set our size in X to be stamp. Our copy benches for rows is the copy SOP that we've got the parameter on. Length is the name of the stamp parameter, and let's give that a default value of 0. And if we bring our visibility down to our benches, there we go. Fantastic. Now, as we saw before when we were dealing with the other way of calculating this, we don't want 100% of this length. So I'm going to take 75% of the length again, as before. So 0.75 times our stamp, and that's going to give us 75% of that length. So yeah, that was a nice and simplified way of calculating this, and just proves again that we have a huge amount of different approaches that you can take to a single problem when working in Houdini.
And it shows you just how powerful it is to create your own custom attributes on the fly,
really
and then use them in such a way that the value, the result of each point that we're dealing with is completely different. It's very cool, very powerful. And with that, is there anything else you want to add?
No, that's absolutely everything.
All right, I guess with this, I don't know which one we'll keep, but in the end, we now have all of our benches copied over to one of the columns.
One row, yeah, for one column,
One
and
column.
we can deal with getting them around in the next video.
Exactly. So with that, that's going to conclude this video. Thanks a lot.